Hello, I'm Michael Simpson, and I'm going to be facilitating this first class for the Climate Resilience Professional Certificate. I'm going to be with you for the next 4 weeks. We actually are going to meet 2 times on 2 different Wednesdays virtually in the evening. And we have participants from across the United States, so you'll be able to get to meet people that you haven't normally networked with, and possibly you will continue networking with after the course. So I'm going to start this presentation, which is just an introductory presentation to get everyone up to speed. So we're all sort of working from the same level of understanding. And this first week, we will have a follow-up presentation by Dr. Eric Osterberg, a colleague of mine at Dartmouth College, who's a climatologist. And he just presented in our climate webinar series a presentation that I think you'll find very interesting. So let's get going. We'll be covering some basics in this presentation, and some of you may find it remedial, but it'll allow everyone to come up to a similar level of understanding. And so beginning with, what is the greenhouse effect? I'm sure everyone knows this, but simply it's caused by atmospheric chemicals, including water vapor, where sunlight as shortwave radiation can pass through, but as that sunlight is absorbed by both land and ocean, it converts and re-radiates as long wave radiation. This is heat energy. And this disperses to the atmosphere and back into the ocean, but cannot migrate well through the greenhouse gases that are in the atmosphere. In short, the greenhouse gases are acting like an insulating blanket holding the heat, in which results in the observed temperature rise over time. Some of the major greenhouse gases are listed here. If one looks at methane, it is a very small concentration compared to water vapor or even carbon dioxide. But when you look at this greenhouse gas, we are actually looking at other factors that need to be taken into consideration when we consider warming of the environment over time. So if you look at this and we go back and look at methane, it is mostly generated by wetlands and from around the world, as well as agricultural systems. It has a global warming potential 12 times greater than carbon dioxide, even though it is in a much lower concentration. But you also know that its lifetime in the atmosphere, the residence time of heating in the atmosphere, is less than carbon dioxide. So we look at these two factors. We look at both the concentration and basically the warming potential of that concentration, and then how long that will occur into the future. So what this tells us is that historic loading of these greenhouse gases are continuing to heat the environment as a result of capturing the long-wave infrared radiation that's trying to get out to the atmosphere and into space. That carbon dioxide causes warming is well established by physics theory and basics, and then decades of laboratory measurements. Now, this has been confirmed by satellite and surface measurements that observe an enhanced greenhouse effect at the wavelengths that carbon dioxide absorb energy. Now, building a case for past changing climate is easier to convince people about than projecting what the future climate may be. But even with this historical data shows us two things. First, on an annual basis, there are variations in the temperature and other climatic factors. But when one looks at a multi-year basis, one can then see a trend that shows us the direction in which these changes are occurring. So, one way to look at it is the squiggles, the variations could be called the weather. And the long-term trend, the direction of the way things are going is what we consider climate change. The other thing to note that the trend itself is increasing at an increasing rate. That's an exponential rate. Thus, looking at past data to project the future may not be the appropriate way in which to model what may be coming. Now, projections of the future is based on modeling. As with all modes of projections, the outputs are only as good as the quality of the input data. Now, models are basically broken up into 4 or 5 overarching categories. Obviously, there's the data, and we always want to know how good is the data, how precise, were the studies done so they could be repeated and be accurate. And then this data is taken into a model, and something is done with it. And, those are the calculations or algorithms. There's sort of the calculations or algorithms for climate models is basically trying to reflect what's happening naturally, not only in the atmosphere, but the relation of the atmosphere to land masses and the ocean. Then you get your outputs. And so once you get your outputs, you have to be very clear in communicating to people who may be using that information what we call the limitations. That is, what was the limits of the data that we used, and what didn't we capture by the calculations in the model itself. And finally, we try to validate the model itself. Is sort of, by creating a model, does it reflect what we are observing in real time or historically over the past. And so validation of models is a way to provide confidence that the results are robust enough to be used to do other things with. Now, modeling the whole Earth is quite complex. There's multiple layers. There's the layers of the atmosphere. There's the relationship of how the atmosphere basically circulates amongst itself, as well as how it circulates around the globe. Okay, and so when we model climate circulation models, we call these global circulation models, or GCMs, and they break the entire Earth into a grid system. And that grid system has not only a axis, XY axis, but it also has a Z axis. And so it basically is going from the top of the atmosphere down through to the Earth and down into the ocean itself. Okay. Now, these three-dimensional columns that stretch from the floor of the ocean and land surface up to the upper atmosphere, these columns are then segmented like a CAT scan to understand what is occurring at each segment or each level, and how each level corresponds with a contiguous segment, both on a horizontal and vertical relationship. Now, you can imagine if you were breaking the whole Earth into these column grids and then breaking each column into multiple slices, that the number of data points and the calculations that show the relationship of one slice to the slices above, below, and to the sides creates a tremendous amount of data that has to be crunched. And so these GCMs are created with by different countries, by different organizations, and they must have supercomputing capability in order to do this. Now, in the United States, we both have the National Center for Atmospheric Research, NCAR, that creates a global circulation model. And then we also have NOAA's Geophysical Fluid Dynamics Laboratory, or the GFDL global circulation model. But there's Hadley in Great Britain and others around the Earth. So they're all trying to come up with a model that closely reflects what is happening in the atmosphere, and then use that model to project what will happen in the atmosphere. Now, the outputs from these models, both current and future projections, is basically things like temperature, precipitation, and other climatic factors. So the outputs are then taken by other organizations and agencies to project potential impacts to their countries, such as the average precipitation to be expected in the future, the frequency of droughts, or frequency of extreme floods, or heat waves, or ice storms, and even how flora and fauna habitat may change over time. You can see that there are multiple global circulation models that are reflected in this graph. And they seem to be quite congruent into the near-term future as far as projections. But variation spread increases further into the future because they are built with different assumptions. But this has been addressed, and they are talking to each other now, and the accuracy of the different models are improving, and they are becoming more congruent in their outputs further out into the future. This shows the spread of different models for the climatic parameters shown that the different GCM model outputs came out with. And you can see that the variation of the spread is getting narrower and narrower as time progresses. In addition, these models are taking into new concepts or new dynamics that they didn't previously take into account. And so as they do new model runs, they're taking more and more complexity into the system. And this complexity is what's contributing to the changing climate. So these models get more and more data loaded because they are taking in other factors that they hadn't taken in before. Now, the code on the x-axis in this diagram reflects the United Nations Intergovernmental Panel on Climate Change, or the IPCC, releases of what we call assessment reports. So that FAR, okay, that's FAR, that was the first assessment report. It was completed in 1990 with a supplement in 1992. The second assessment report, SAR, was 1995. TAR was 2001. AR4, the fourth assessment report, was 2007, and currently we're operating on AR5, which is released in 2014. However, supplemental reports are being released by the UN, and the AR6 should be out in 2021 or there soon after. And each time they do a new reiteration of the modeling and come up with a new assessment report, they have taken into new areas of dynamics that are occurring between the climate and the other systems on Earth. But what has been improving with the assessment reports over time is the granularity of the outputs, because they have been taking into not only new factors, but they also are creating much tighter grids, that is, much smaller area grids and columns. But you can imagine by creating more columns and slices, you're adding a new set of data and calculations that need to be crunched by the supercomputers. But the outputs, what it is doing is basically allowing us to make better demarcations of where things will happen when in our planning. And so we get much refined outputs spatially as a result of the maturing of the modeling from the global circulation models. Now, as scientists such as our group at the Center for Climate Preparedness and Community Resilience, we take these global circulation models and we downscale. We basically take what the UN has provided us, and then we try to translate that down to a much smaller scale that's really applicable to planning and management. And so we've been able to downscale these models to the watershed level for our research. An example of this is a research project we did in our neck of the woods in Keene. We were looking at the impacts to water conveyance infrastructure, that is, how do you deal with runoff in the context of a changing climate. Now, in order to transfer the GCM projections to Keene, we model how the intensity return period, or basically what we're talking about is the frequency of certain size storm events, okay, changed from the late 20th century, and we were going to project what was going to happen by mid-21st century. So in our area, there's 6 GMC grid points surrounding Keene, okay, and that has data that we look at that we need to measure in order to translate it to weather data that's historic, very close to our study area. And so we look at factors such as longitude, latitude, elevation, and several other factors which we call shape parameters, and statistically downscale the system. And then we see how close measurements are between the GCM grid points when we apply our shape parameters and the weather stations around Keene. And thus we come up through regression analysis of how tight a fit we have. And so that little circle around those weather stations were the weather stations that showed a high congruence with the GCM points, which are the red dots. And so we could be pretty confident that within that circle, our projections are reflecting global circulation models down to the river basin and watershed scale. Now, once we had our model, what we were trying to do is to validate it. That is basically, how well would this model project the future? So what we did is we took historic data from the 1920s, historic weather data at those climate stations, or those weather stations from 1924 roughly to 1959. And then we tried to project what would be the weather, and we were looking at a rainfall amount for a 24-hour storm event that occurs with a 4% probability, or we call that the 25-year storm. We were going to say, you know, if we take that historic data and we put it in our model, can we project what would happen for that kind of rainfall probability from 1970 to 2000, which we have good records of. And so we took really old historic data, put it in our model to project what would happen in newer historic data. And so this little curve here basically is showing how tight a fit our model projections were to what actually happened. The solid line is basically actually showing you what the precipitation amounts would be for different type of storms, 21, you know, the 1-year storm, the 10-year storm, the 100-year storm. And that's what we were trying to calculate. And the dashed lines, both A and B, are basically the 2 model runs to see you know, how tight a fit it was. And at the 24-hour, 25-year precipitation amount, we only saw a 3% variance between what actually happened and what our model projected. And so with that 3%, we felt that was reasonable to use the model now to take it and apply it to what we may think would happen in mid-century as far as the intensity of rainfall for a 24-hour, 25-year storm event, and then use that in other models to model runoff and infrastructure capacity. Now, in all this modeling, the greatest unknown about the future is, what will we do? which brings uncertainty into any future projections. This graphic shows possible greenhouse gas loadings into the future based on different sets of assumptions. And each line that's coded is basically making assumptions about human and societal behavior. The set of assumptions were created by the UN in 2000 in a report called the Special Report on Emission Scenario series, and it basically was coming up with a net greenhouse gas loading, that is greenhouse gas loading subtracting possible sequestration of greenhouse gases. Now, the assumptions are not only based on decisions of what we would do in regards to development, population growth, natural resource management, and environmental emissions, but it also would look at, how would we operate as a society? Would we be global or would we be regional? Will we have standardization globally, or will we have a potpourri of regional approaches which would have different outcomes? And so the storylines came up, okay, and those storylines were quite different as far as how energy intensive, how global they were, how regional they were. Was populations leveling out or growing? Was consumerism increasing or leveling out? It really addressed it from a global perspective, but did not take into account the equity of resources amongst subpopulations. And thus, those assumptions went into the assessment reports to get the different projections into the future. Now the outputs are known as RCPs, okay, which are representative concentration pathways, and it is basically how much carbon dioxide like gases will be loaded in the atmosphere to create the radiative forcing that causes the heating. And if you look into the future, as I said, these models, these projections about the future are quite clustered together. And so into the near-term future, we're pretty much on a single path, but based on continued decision making, we could separate where the green curve shows a very optimistic future where we're very proactive and consider climate change an emergency, to the red line, which is basically a business as usual. We really haven't changed our behavior, and you're going to see CO2 concentration, thus temperature increase, and thus a change in all the other climatic parameters that are being projected into the future. So just consider that once we get to the point that we're on one pathway, if we get on the red pathway, it's going to take a lot more resources and effort and coordination to get off that pathway and jump onto one of these other curves that are a little more optimistic and flattening out. Now, dealing with uncertainty by these analysis, Antioch researchers have come up with modeling and downscaling that is what we call scenario analysis, that we just don't choose one pathway because as scientists, we can't judge what risk others want to live with. And so we bracket our research by population growth and have a very what we call pessimistic future. And then on the opposite side, we'll look at our analyses, what we would consider the very optimistic future. And by bracketing optimistic with pessimistic, you can see there's the range of what's the likely outcomes based on the assumptions we put into the model. And then whoever we're doing the work for can decide which results they want to consider when they come up with plans and adaptation strategies. Now here's an output from one of our research studies not too far north of here. And what I really want to show here is, one, you can see that we were projecting the 25-year, 24-hour precipitation event. Why we were doing that is because this study was going to look at the capacity of road crossing, culverts, and bridges. And that was the design storm engineers use to build the infrastructure that's already in place. And so you can see we ran a number of runs of what that precipitation would be like through our climate downscaled models. And we have the baseline, which is the historic, and then we have the B1, which is the optimistic, and we have the A1FI, which is the pessimistic future, and the A1B is sort of in between. So we ran, these four scenarios. Now, you can take the most likely output, okay, and say that's what's going to happen. But as scientists, we actually look at the range of possibilities and how confident we are. And so we have confidence intervals. In this case, we're using the 95% confidence interval, that anything within the range of the 95% confidence interval could occur. And the issue is, what scientists produce and what engineers want are quite different. Okay, the engineers want a number. They want a very specific number that they can grab onto to put into their designs to build infrastructure. And so often they'll take the mean. Okay, they'll take the middle numbers. Okay, but the upper confidence intervals, the amount of rainfall that can fall in 24 hours for a 25-year storm event, can be quite high. In fact, if you look at the A1FI into the future, the upper confidence interval is 11.10 inches into 24 hours. And to be honest with you, we've already had 2 of those in this neck of the woods since 2000. So it's as likely to have that as to have the 4.34 or the 6.65 with a 95% confidence. But as I said, engineers need a specific number. Okay. Now, for example, when engineers are dealing with water and designing anything that deals with water, dams, bridge openings, culverts, stormwater systems, they basically need to have a rainfall amount. So they have to decide what design storm are we going to use. And so for culverts, for example, they use the amount of rain that falls in 24 hours that is the 25-year storm event, or a 4% chance of occurring in any one year. So what they do is they go to NOAA, okay, the National Oceanic and Atmospheric Administration. Under their weather.gov and their climate stations, they basically have taken historic rainfall, okay, and they've statistically analyzed what the frequency of a 4% storm would be, and they give them a number, okay, and so they get a number from NOAA. It says 3.5 inches, and this is what they grab on, and this is what they have grabbed on to, and they design all the infrastructure, water conveyance infrastructure we live with today. Well, as a scientist, we went into those numbers, and we found that if you looked at the 95% confidence interval, the range was, spread was 58% between the low and high values. And so, that's not very precise, but, engineers are communicating to their clients and to communities that, I have a stamp, I have an engineering license, and the numbers I've chosen are precise, and I have confidence in those numbers. And so the reality is, the engineers are communicating a sense of certainty, and they feel confident in their design and construction to the point that they could sign and stamp their plans. But in fact, the engineers really have been conducting the design and construction analysis under uncertain conditions. In fact, all our infrastructure has been designed under uncertain conditions. So we wanted to investigate, sort of this uncertainty about climate futures and modeling climate futures versus, off-the-shelf engineering design. So one of the research projects we did was out in the Minneapolis region, where we were looking at stormwater systems and when will they be undersized for future rainfall amounts. But one of the key questions we had as scientists was basically, if we validate the model, the climate model, and compare it to the engineering model, which is off-the-shelf engineering tools, what is the level of uncertainty when you compare projecting something into the future using climate models versus standard engineering protocols? Now, this study did a multiple set of things, not just looking at stormwater, but we were looking at land use decision making, utilizing stormwater mitigation strategies such as green infrastructure, and we were doing associated cost analysis for impacts into the future. In regards to impacts from precipitation, there were two different steps in the modeling. Okay, one was basically our analysis of the precipitation into the future using GCMs and downscaling those to apply specifically to our study site. And so that was a model that I previously talked about. The second was using off-the-shelf software. In this case, it's known as SWIM, S-W-M-M, that engineers use to take that precipitation number and taking land characteristics, they translate that into runoff. And that's the runoff that goes into the stormwater system that were historically designed for our study area. And so we have two models that we were depending on in order to come out with how impacted would the stormwater system be in this region. So some of the outputs, just to show you, is, if you look at the percentage of undersized stormwater components, that is undersized stormwater pipes in Minneapolis, for example, it's a straight engineering relationship between the amount of rainfall that falls, okay, and then gets changed through SWIM, the engineering model, to runoff. And so as more rainfall falls, more runoff is going to occur, thus more pipes are going to be undersized. And this just basically shows the outcomes for our optimistic, what percentage would be undersized into the future for optimistic versus the pessimistic, okay, projections of rainfall. Okay, straight engineering relationship. The bottom curve is basically something that was what we were really looking at, is what are the impacts, how vulnerable is the community to such undersizing of pipes. And so we were looking at flooding after the pipes were filled, that is, they were under capacity, and that runoff no longer went into the stormwater system, but started to build up on the streets. And so the red line is basically flooding on the streets. And the black line is the amount of floodwaters that occurred. The difference is that amount of water not only flooded the streets, but went over the curbs and projected to impact structures. And thus, that's where the cost analysis came. And so that's basically the two models we used, okay? And we started with the downscale precipitation model and fed that model into the engineering model. And so you can see, just like I talked about, we had tremendous amount of different runs of models, okay, and different climate scenarios we were using. These are different types of models and scenarios. And so we were running a lot of scenario analysis, but what we did find is, from the optimistic future, we saw about an 18% projected increase in rainfall amounts. For the pessimistic, we saw about 153% increase in rainfall amounts over baseline. So 18% optimistic, 153% pessimistic. The range between that is 135, or basically uncertainty in our precipitation modeling of about 135% between optimistic and pessimistic. And so, you know, applying that to the engineering model, we could spatially show what was happening to the city, and the red is basically where the over-curve flooding would occur at different rainfall amounts coming through our rainfall model and then going into the engineering runoff model. But if we start to look at the uncertainty of the two, what is very clear is that the uncertainty, overall uncertainty of the precipitation model was much smaller than the overarching uncertainty of the engineering model when we validated it. Is basically, you know, we talked about the validation of our climate downscaling, but we also validated the engineering model by basically looking at how well the model worked for the stormwater system, and then looked at historic flows or outflows of that stormwater system to see how well it predicted them. And so the off-the-shelf engineering model was not as certain, but we use this every day all over the United States to design our infrastructure. So in short, you know, our society has been designed and built on such uncertainty. And we just need to understand that, you know, when people say, well, how uncertain are you, or how certain are you about the future climate? I said, well, how certain were we about building the society in which we live in now? And so the one take home is what creates vulnerability is not the uncertainty about the future. It is the shift in the overarching climatic system where the historic designed infrastructure is under capacity for the new normal. And so I will just leave it there, and I do hope that that you will enjoy the course and use some of this information to possibly inform some of your assignment or feedback that we will be asking you for over the next couple of weeks. Thank you, and have a nice day, and I'll see you next Wednesday in a Zoom meeting so we all can see each other and meet each other.